Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, lesson 33, the definition of a parabola. Classwork opening exercise says, suppose you're viewing the cross-section of a mirror. Where would the incoming light be reflected in each type of design? Sketch your ideas below. So we were given these light blue arrows coming down. That's the incoming light. So I have extended them down to the surface of the mirrors. And as you can see, they're coming down and just touching this flat mirror here. Mirror 2 is shaped like a V or an absolute value function. And mirror 3 is shaped like a parabola. Okay. So what would happen if the reflection, what would happen to the reflected light after hitting each of these surfaces? Okay, so here is what would happen with mirror 1. The light would just reflect directly back up to its source. Okay, this mirror here, this ray would come down and hit, and then at the same angle, this angle would equal this angle, it would shoot over and hit the other mirror. And that would bounce off and go up again, but we're only going to focus on where they hit the mirror again. So there is the reflection in red. And now the mirror 3, which looks like a parabola, would look like this. Okay, so each of these would bounce off, but the interesting thing that occurs with a parabola is they all bounce and they hit a point right here, all of them reflected up to this point. So if I didn't extend these red lines, they would have all stopped right here. And that is called our focus. That is the focus point of a parabola. All right, page 2 is just a discussion page. So a telescope design. When Newton designed his reflector telescope, he understood two important ideas. Figure 1 shows a diagram of this type of telescope. The curved mirror, okay, parabolic mirror, primary mirror right here, the curved mirror needs to focus all the light to a single point that we will call the focus. So he wanted this mirror to curve so that when the light hit it, no matter where the light hit it, it would reflect up and hit at the exact same point up here at the focus. An angled flat mirror is placed near this point of focus and reflects the light to the eyepiece of the telescope. Okay, so then there's a mirrored flat surface at the focus point so that all that light gets turned and put to the image plane up here, which is the eyepiece. The reflected light needs to arrive at the focus at the same time, otherwise the image is distorted. Okay, so by definition, a parabola with directrix L, this is this line right down here. There's a line parallel to the x-axis down here, okay? With the directrix, let me get my pen out. So it says a parabola with directrix L, which is right here, and a focus point F, which is right here, is the set. So the parabola is the set of all points in the plane that are equidistant from the point F and the line L. So a parabola is a lot like a circle. A circle, by definition, is the set of all points equidistant from its center. In the case of a parabola, the parabola is the set of all points equidistant from the focus and the directrix. So this line Q1 that goes from this point Q1 that goes from Q1 to P, this distance right here is equal to the point or to the line FP prime or P1. FP1 equals Q1 P1. The line segment that goes from Q2 to P2 is equal to FP2. And this line here, Q3 going up to P3, is the same length as FP3. So if I were to label these as congruent, this would get 1 mark, that would get 1 mark. They are the same length. This would get 2, this would get 2. Those are the same length. This would get 3, this would get 3. Those two line segments are the same length. So every single point on this parabola is going to be the same distance from F and L. So if I then, for example, drew one more line segment, let's do it in red, and I started right on the F and I go over like so, then that line segment I just drew would be the same length as this line segment down here. No matter where you draw, every single point on the parabola will be the same distance from the focus and the directrix. Okay, continuing on, it says figure 2 to the right illustrates this definition of a parabola. In this diagram, FP1 equals P1Q1, FP2 equals P2Q2, FP3 equals P3Q3, as I stated earlier. Showing that for any point P on the parabola, the distance between P and F is equal to the distance between P and the line L. All right, so a parabola, all parabolas have the reflective properties illustrated in figure 3. Rays parallel to the axis, the y-axis that is, reflect off of the parabola and through the focus point F. Thus, a mirror shaped like a rotated parabola would satisfy Newton's requirements for his telescope design. Okay, page 3 shows figure 4 and figure 5. Figure 4 below shows several different line segments representing the reflected light with one endpoint on the curved mirror. That is a parabola and the other endpoint at the focus. Anywhere the light hits this type of parabolic surface, it always reflects to the focus F at exactly the same time. Figure 5 shows the same image with a directrix. Imagine for a minute that the mirror was not there. Then the light would arrive at the directrix at the same time. Since the distance from each point on the parabolic mirror to the directrix is the same as the distance from the point on the mirror to the focus, and the speed of light is constant, it takes the light the same amount of time to travel to the focus as it would have taken it to travel to the directrix, okay? So what they're saying is if this light continued from here down to here, and this one continued from here down to here, and so on, they would all hit the directrix at the same time. And since this distance is equal to this, and this distance is equal to this, if they reflect and go to the focus instead, these 5 distances are equal to these 5 distances. So therefore the light would reach the focus at exactly the same time. All right. So it continues on to say, where was I? Since the distance from each point on the parabolic mirror of the directrix is the same as the distance from the point on the mirror to the focus, the speed of light is constant. It takes the light the same amount of time to travel to the focus as it would have taken it to travel to the directrix. In the diagram, this means that AF equals AF sub A, BF equals BF sub A, or I'm sorry, sub B, and so on. Thus, the light rays arrive at the focus at the same time, and the image is not distorted. Okay, so now we're getting on to an example. Finding an analytic equation for a parabola. Given the focus and directrix, create an equation for a parabola. So they're telling us the focus is at the point 0, 2 on the y-axis at the y value of 2. So the parabola is a set of all points. So P equals a set of all points x, y, such that those points x, y, each point x, y is equidistant from F and the x-axis. So in this case, my parabola crosses at 1. So this is a distance of 1. And from 0 to 1 is 1. So these are equal. So this means that our focus is at point 0, 2, and our directrix is the x-axis. Okay, so it says let A be any point x, y, right here on the parabola. Let F prime be a point on the directrix with the same x coordinate as point A. So if I come over here 5, if x was 5, then this would be the point 5 comma some y. on the parabola. So it says, what is the length of A, f prime? Use the distance formula to create an expression that represents the length AF. Okay, when you have a vertical line, it's really easy to find the distance. It's just the change in y, because the change of x is nothing. All right, so I'm going to show it though. The distance formula is d equals the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. So over here, I'll write my 2 points. Okay, this is point 1 and this is point 2. So point 1, what are we trying to find? The length of A, f prime. So let's call A point 1, and that's the point x comma y. And point 2 is down here, f prime, and that's going to be the point x comma 0. So when I substitute this into the distance formula, we're going to get, okay, let me just create this. All right, so it's x2, which is x, minus x1, which is x. So it's x minus x. And then it's going to be 0 minus y. So the distance is going to equal the square root of, well, x minus x is 0, and 0 squared is just 0. So that goes away. And 0 minus y is negative y. So I'll just write that just so you see it. So we're just going to end up with negative y squared. So the distance equals the square root. Well, negative y squared is going to be y squared when you take it out of the parentheses. Negative y times a negative y is y, and it's squared. And the square root of y squared is simply y. So the distance from here to here is our y value. So in other words, let's just give you an example. If this was the point 1, 2, 3, and this is 1, 2, 3, 4, then this would be the point 3, comma 4, and this would be the point 3, comma 0. Okay, so if I put that in the distance formula, it'd be 3 minus 3 squared, which is 0, plus 4 minus 0 squared, which is 4 squared, which is 16, and the square root of 16 is 4. So the distance is just simply the length of the line counting from 0 to 4. All right, so let's just get rid of all that. So there's the length of A f prime. It's y. Okay, so A f prime equals y. So I'll say that A f prime equals the length y. Then it says use the distance formula to create an expression that represents the length of AF, which is this. All right, so I'm going to say AF equals the square root of, and I put that in, and it's going to be x2, which is here, which is x, minus x1, which is 0. y2 is y. y1 was 2. So AF is going to equal the square root of x minus 0, which is simply x squared plus y minus 2 quantity squared. That's the length of AF using the distance formula. Okay, so now it says to create an equation that relates the two lengths and solve it for y. So if I go back here at the bottom of the last page, AF is this equation here. So I will copy it and bring it over to this page. Okay, so there is my AF. I'll put it right here. And the other one, AF prime, is right here. So I'll bring this over. All right, so what we know is they're equal to each other because of that definition. So since AF prime equals AF, then they're going to be equal, then Y is going to equal this equation. So we're going to write Y equals the square root of x squared plus y minus 2 squared. Okay, I want to get rid of this square root, so I'm going to square both sides. So when I square both sides, I'm going to get y squared equals, and everything under here is just going to be without the radical, x squared plus y minus 2 quantity squared. Okay, and then I'm going to do the distributive property here. So I'm going to write y squared equals x squared plus y squared minus 4y plus 4. All right, so now I'm going to subtract y squared over to the other side, and we're going to get 0. Okay, so we're going to get let's see, if I subtract y squared over, it's going to be 0 equals x squared minus 4y plus 4. Okay, hopefully you saw that, minus y squared and a minus y squared. These will cancel. This will be 0 over here, and that's what I have here. So I'm going to move my minus 4y over to the other side. Add 4y to both sides, and we will get 4y equals x squared plus 4. Divide both sides by 4, and we're going to get y equals 1/4 x plus 1. 1/4 x squared, I mean. Okay, so there's our equation. So it's a parabola with a y-intercept of 1, and my a is 1/4. 1/4 x squared plus 1. Okay, so I brought the graph in here, and now we're going to verify that the equation appears to match the graph shown. So it's a very lengthy explanation, so I brought it in as text. It says, consider the point where the y-axis intersects the parabola. Let this point have the coordinate 0, b. That's right here. I'm sorry, no, it's not. Let me get rid of that because it's blue for starters. So let's do a point. So it says, consider the point where the y-axis intersects the parabola, which is right there. We're going to call that point 0, b. From the graph, we see that b has to be between 0 and 2. The distance from the focus, 0, 2, to the point 0b is 2 minus b. Okay, so if this is the point 0, b, and it's a vertical distance, then the distance is the distance between y2 minus y1, so it's 2 minus b. And the distance from the directrix to 0b is also going to be b units. So this distance is equal to this distance because of the definition of the distance of the parabola from the focus and the directrix. So since 0, b is on the parabola, we have 2 minus b equals b, so that b equals 1, adding b to both sides. 2b equals 2, and so on, okay? From this perspective, we see that the point 0, 1 must be on the parabola. Does this point satisfy the equations we found? Let x equal 0 and see if you get a 1. So if I substitute in 0 to this equation, we'd get y equals 1/4 x squared plus 1 would equal 1/4 x is 0 squared plus 1. And 0 squared is 0, 0 times 1/4 is 0, 0 plus 1 is 1. So the point 0, 1 does satisfy this equation. This is the only point that we have determined to be on the parabola at this point, but it provides evidence that the equation matches the graph. Whew. Okay, exercise 1 says to demonstrate your understanding of the definition of a parabola by drawing several pairs of congruent segments given the parabola, its focus, and directrix. Measure the segments that you drew to confirm the accuracy of your sketch in either centimeters or inches. I prefer centimeters, so we aren't dealing with decimal or fractions. And so let's just start off by measuring right here. So we're going to try to be really accurate. trying to move this a little bit. Come on. Right there. Perfect. Okay, so now when I measure this, let's use green. This is 1 centimeter. So as you can see right there, from the focus to the parabola is a distance of 1 cm. So if I drew a segment there, that is distance 1 cm. And then as you can see from here down to here, we get to 2. So this is also a distance of 1 centimeter. So I'll do this one in purple. This distance right here is 1 centimeter. All right, so I could label those 1 cm and 1 cm. Okay, so there's the point that is equidistant from the directrix and the focus. So what I'm going to do now is I'm going to try to find another place, and I'm going to try to make it pretty accurate that it's right on a segment. So I'm going to rotate this around. Accuracy is key. All right, so I'm just going to rotate it until I get to 1.5, and I'm off the grid, unfortunately. So how about I go out to here, which is 0.7 centimeters or 7 millimeters. Okay, and I'll draw a segment. So let me get this out of the way. So I'm going to draw a green line. Green. And I'm going to draw it from here to here. Came up a little short. So drawing a segment from there to there. As you can see, I'm at 7 millimeters. Then if I take my ruler and rotate it back like this, and then measure from that point right there down, and I measure it, that is also a distance of 7 from here to here. So that's 7 millimeters. So there's one. So this is 7 millimeters, and that's 7 millimeters. Okay. It says to do several pairs. Let me do one more. So if I put this here, let's go over to this side this time. And I'll go out like so. So this is 5, 6, 7, 8. So this distance is 8. I'll do it in green again. From there to there is a distance of 8 millimeters. Move this back down, bring it over here, draw a segment down. And as you can see, measuring that, we are at 5, 6, 7, 8, give or take, okay? The accuracy is hard to do on here. On paper, it'd be easier. So that's congruent to that. So as I go out, then our point's going to be on the blue parabola are going to be the same distance from our focus and our directrix. Okay, page 5, number 2. It says to derive the analytic equation of a parabola given the focus of 0, 4 and the directrix y equals 2. So the directrix is right here, and this is the focus right here. Use the diagram to help you work this problem. It says to label a point x comma y anywhere on the parabola. I'm just going to label its vertex. Okay, so that's right here. And that is the point 0, 3. All right. So it says label a point xy anywhere in the parabola. There it is, 0, 3. Write an expression for the distance from the point x comma y to the directrix. So the distance from here to here, x comma y to the directrix. So it is going to be some y value minus 2. no matter where it is, okay? If I pick the point over here, and this is the point 2 comma 4, oops, not 2 comma 4D, 2 comma 4, okay, then the distance from here to here is the y value minus 2 because the directrix is 2. So 4 minus 2 is 2, 3 minus 2 is 1. So the distance is your y value minus the 2. So it's y minus 2. Part C says, write an expression for the distance from the point xy to the focus. Okay, just to make things a little more interesting, I will use the 0.24 for this. Okay, so the distance from here to the focus would be, well, the y values are the same. So in this case, 4 minus 4 is 0. So the expression for the distance from the point x comma y to the focus would be the square root of y2 or x2 minus x1. So x2 is 2, x1 is 0. So that'd be 2 minus 0 squared plus y2 minus y1, which is 4 minus 4 squared. Okay. But if we're just talking about the point x comma y, then we would change our numbers. Instead of using the point 2 comma 4, we'd use the point x comma y. So it'd be x minus 0 squared plus y minus 4 squared square root. So part D says to apply the definition of a parabola to create an equation in terms of x and y and solve the equation for y. So all they're telling us to do is take our equation from B and set it equal to our expression in C. So it'd be y minus 2 equals the square root of x minus 0 squared plus y minus 4 squared. Okay, so the first thing I'm going to do in this one is we're going to solve for y. I'm going to take the square, I'm going to square both sides to get rid of that radical. So in doing that, I'm going to get y squared minus 4y plus 4 on the left when I square that. And over here, I'm just going to get x. Let's get rid of that minus 0 at this point. I'm just going to get this x minus 0 squared, or just x squared, plus y minus 4 squared. So then to simplify that, we get y squared minus 4y plus 4 equals x squared plus, and then when I square this, I'm going to get y squared minus 8y plus 16. All righty, so if I subtract y squared over to the other side, those are gone. Add 8y to both sides will give me a positive 4y over here. And that is going to, at the same time, I'm going to subtract 4 over here. So that's going to leave us with x squared, and 16 minus 4 is 12. So I'm going to get 4y equals x squared minus 12, divide everything by 4. And that will give me y equals 1/4 x squared minus 3. And there's the equation of our parabola. Okay. Actually, it's not minus. What did I do here? Oh, 16 minus 4 is not negative 12. It's positive 12. So then it's plus 3. So the reason I knew that was wrong was because that's my y-intercept. My constant is my y-intercept. It was positive 3. It was not down here. Negative 3 way down here. So this is the equation. Okay, part E. What is the translation that takes the graph of this parabola to the graph of the equation derived in example 1? Let's go back to example 1. Okay. Where is example 1? Oh, it's on the same page? No. Okay. Where is example 1? Keep going. Example. Exercise 1. Okay, they didn't call this example one here, but I guess this is it right here. So our equation is y equals 1/4 x squared plus 1. And now we have 1/4 x squared plus 3. So that would be a shift down 2. So the graph of the parabola to the graph of the equation derived in example 1. So in other words, we're taking y equals 1/4 x squared plus 3, and we're translating it to y equals 1/4 x squared plus 1. That would be a shift down 2 units. Okay, just moving that y-intercept from 3 down to 1 would shift it down 2. Okay, page 6 brings us to the end of lesson 33. Review the lesson summary and go to your problem set.